Hi guys, today we're going to talk about random variables. So far we've been talking about probabilities of some space omega. So we have this universe omega, is our universal set. And then we have p as a probability on omega. And so remember that p is a map from the power set of omega. And so far everything we've looked at, the power set's been fine. So it takes the power set of omega to the interval 0 to 1. So it's a map and it has some special properties that we defined before. So what is a random variable? It's another function. So a random variable is a function which I'm going to write as a capital X. So I use bars to denote capital letters, and that way you don't get it confused with a lowercase x. So a capital X, which goes from omega over to the real numbers. So remember that this r represents just the real number line. And this is not the power set of omega here. So p takes in subsets of omega, but x just takes in points in omega. So that's what a random variable is. It's just a function that takes points and maps them to real numbers. So let's do an example. Say we flip a coin 3 times. So omega, the universal set, is the set of all outcomes of coin flips. So there's 8 outcomes for 3 flips of a coin. We could get 3 heads, 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 tails, heads, tail, heads, and then heads, tail, tail. And then let's just flip the roles of heads and tails here. We could get 3 tails, tail, tail, heads, tail, head, tail, or tail, head, head. So the first letter represents the first flip, the second letter is the second flip, and so on. So if I flip tails, heads, tails, that would be this one, tails, heads, tails. If I flip heads, tails, tails, that would be this one. So this would be heads and then tails and then tails. So that's omega, is just all possible outcomes from the 3 coin flips. Now we can put a probability on omega, and we can define the probability for each point. So the probability of any point I, so the probability of x, the set x, which is equal to, usually we just write that as the probability of x is just 1 out of 8 for all x in omega. So, right, the probability I get any one of these, that I get 3 heads, for an example, is just 1/8. And the probability that I get, say I want to compute the probability I get a tail on my last flip, so I could compute that by heads, heads, tails, heads, tails, 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 and tails, heads, tails. Which then equals, so these are mutually exclusive events, I can't do each of them, so it becomes the sum, the probability of heads, heads, tails, plus the probability of heads, tails, tails, plus the probability of tails, 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 plus the probability of tails, heads, tails. So this equals, what, 1/2. Right, there's a 1/2 chance the last flip is the tails. Okay, so that's our probability in our space. But now we want to define maybe a random variable on this space. So suppose we wanted to count the number of heads. So let x be the number of heads flipped. So notice that it satisfies the definition. X just goes from omega over to the real numbers. Okay, so what is x? Well, we can define x just point-wise. So x of heads, heads, heads equals 3. X of heads, heads, tails equals 2. Right? X of heads, tails, heads equals 2. And so on. X of heads, tails, tails equals 1. And maybe we'll do x of tails, tails, tails equals 0. Okay. And you could just figure it out for each point. You just count the number of heads in the sequence, right? So that's what a random variable is. And of course, we're often concerned with random variables. We don't too often care about the actual outcome, but we care more about some function of the outcome. So for example, if we're playing a gambling game and we win $1 for every heads flipped, then maybe x represents the number of dollars won. So, if you get all tails, $0, but if you got 2 heads and then a tails, you get $2 or something like that. So x takes the actual data, the heads and tails, and maps it to some number, r. And so that's what a random variable is just a map from the actual outcome data to the real numbers somewhere. And now then we might want to ask something about the probability of an outcome for the random variable. So remember that x is a function, but usually we don't put in the input. So usually whenever you write functions, you write something like f of x. But we just get rid of this part. So usually we'll just write f instead of f of x, unless you're actually plugging something in for f. Okay. So let's see. I'm going to keep using this example. So x is the same thing it was that I just erased. That's just the number of heads flipped. So we could ask, what is the probability that x equals 1? So remember, x is the number of heads flipped. And what are we doing? We're flipping a coin 3 times here. So what this represents, this symbol, stands for the probability that I get 1 heads if I flipped the coin 3 times. And how does this make sense? So what do we mean by the probability that x equals 1? So remember what p does. P is a map from the power set of omega to 0, 1. So the input here is a subset of omega. We have to find some subset here. Well, what we do is whenever we say this x equals 1, this is actually representing a set. It's the set of points that make x equal to 1. So in other words, it's the set of the preimage of 1. So what gets mapped to 1 by x? Well, x of heads, tails, tails equals 1, right? So for example, we have HTT in the set because x of HTT equals 1. Also, x of tails, heads, tails equals 1. So we would put tails, heads, tails in the set. And then we would have tails, tails, heads in the set. So these are all the points that x would send to 1. So these are when x equals 1. And so whenever we say the probability that x equals 1, what we really mean is the probability of the points that make x equal to 1. So the probability of HTT, THT, and TTH, which in this case would be there's 3 points and they each have probability 1/8, so it's 3/8. So there's a 3/8 probability that we have 1 heads. Okay, and to do this slightly more generally, which I've got a few minutes, so if omega is any space, and we have some probability p, which goes from the power set of omega to 0, 1, and then we have, so omega is our sample space. So that's our probability. Then we can have a function x which goes from omega over to the real numbers. So this is a random variable. And then we can take A to be a subset of R. Now, just like I'm being I'm a little bit loose with the probabilities. So I mentioned in the first video that we don't actually use the power set of omega in a higher level class. Likewise, x can't just be any function from omega to r, but for this class, we're not going to get that technical. So for now, we'll just take x going from omega to r, and we take any subset of the real numbers. So if we take any subset A of the real numbers, we said that the probability that x is in A, so we let the set of x belonging to A, now this is a function, but this just means the set of points in omega such that x of omega is in A. Or another way to write this is the preimage of A. So everything in omega that gets mapped into A. So we talked about this in discrete math and used this notation a little bit. But you might not remember it. It's just whatever things get mapped into A. And so the probability that x is in A is just the probability of this set, or the preimage of A, if you like. And whenever we say the probability that, for example, x equals some little point x, maybe, this is the probability that x lands in the point that only has x inside of it. So same thing. And we might do something like the probability that x is less than little x, which is the same thing as the probability that x is in the interval from negative infinity to x, and so on. So this notation really covers what we mean by probability that a random variable takes certain values. All right, so we'll elaborate more on this in class, and I guess I'll see you guys soon.